The other main type of light source that we can use is a monochromatic light source, something that emits a specific color of light. And the most common monochromatic light source is a laser. And I love lasers because they are something that I use every day for my research. And they have a lot of really awesome properties. Now, for general purpose spectrophotometers, it doesn't make sense to use a laser. Lasers can only emit one specific color of light at a time, versus a broadband lamp where we can use a monochromator and get any color we want, essentially, throughout the visible or ultraviolet range. But for specific applications, specialized applications, lasers provide a lot of advantages that you don't get from a typical lamp. So we'll briefly talk, only briefly, about how a laser works. The main idea is we have several energy levels in our system, whether these are electronic energy levels or vibrational or semiconductors. But the idea is that we have several energy levels, and the main thing we need is two energy levels where we can make it so that there's more molecules or whatever it is that we have that are in the excited state than in the ground state, or I should say lower state, typically not the ground state. And that's called a population inversion, where you have more molecules up here than you have down here. And what you can do when you achieve this population inversion is that you have what's called stimulated emission, where a photon that matches this energy gap can cause light to be emitted. We often think of light being absorbed when we have a photon that matches an energy gap, and that's what we rely on for spectrophotometry. But you can also have emission caused by that, kind of the same idea but in reverse. And so this stimulated emission of radiation, light amplification by stimulated emission of radiation, can lead to you have the more light you produce, the more light you get, and you get lots of light at a specific wavelength. So that's the very basic idea of how a laser works. Now, the properties of a laser that are really useful are that it has this one specific color of light, so you don't need a monochromator, and you can get a very, very specific color of light if you need that for your application. One of the big advantages is that it's extremely bright, much brighter than a lamp. You never want to look into a laser. That's one of the main dangers of a laser, is that can lead to vision loss. But you get lots of light at a very specific wavelength. And that can be very useful when you're trying to measure something that's not highly concentrated in a sample that you're trying to measure. And that's one of the things that we take advantage of in my lab. Laser light is collimated, which means it travels in a column or in a specific direction. And so you can use that to manipulate the light and move it around, a table. Say you can do that with a lamp as well, but you don't get as much light to work with as you do that. You have to throw away a bunch of the light. Laser light is also polarized, which can be useful for specific applications, meaning all the electric fields oscillate in a specific direction, either up and down or left and right, something like that. And laser light is coherent. Again, this is relevant for some specific applications, but all the waves are in phase, so they don't beat out of phase. In comparison to regular lamps, where it's just incoherent, and the waves are just kind of random. The same with the polarization. So laser sources are available across the electromagnetic spectrum, from ultraviolet to infrared. So we could have a whole class just on types of lasers and how they work and different things, because there's a wide range of different types of lasers that have been developed over the last 60 years, 60, 70 years or so. But anyway, in terms of spectrophotometry, it's really these properties that can possibly make them useful for specific types of spectrophotometers.